A concrete column of cross-sectional area 400 by 400 mm, reinforced by 4 longitudinal 50 mm diameter rod steel bars placed at each corner of the column, carries a compressive load of 300 kilonewton. Calculate load carried by the material and compressive stresses produced in each material and load shared by the material. Take Young's modulus is equal to Young's modulus of steel bar is equal to 15 times of Young's modulus of concrete. Assume the height of the column is 2 meter. So this is the given problem. Now we have to solve this given problem. For solving this problem, first of all, the first step is, several times I have repeated, first of all, you have to write the given data properly. So in a single units. So same thing I have done here. Area of the steel rod, AS is equal to, it's a circular in nature. Cross-sectional area is 50 mm square. Here pi by 4 into ds square, pi by 4 into 50 mm diameter. I have substituted here and I got 625 pi mm square. And similarly, area of the steel rods. So there are 4 steel rods, 1, 2, 3, 4, 4 bars of 50 mm pi. So therefore, so the total area of steel bar is 4 times of area of single steel bar, that is 4 into 625 pi. So this is 250 pi, and the pi to 2500 into pi value 3.14, you will get 7852.5 mm square. So once you got this, next given data, area of the concrete. So this is the concrete column. So area of the concrete column, its dimensions are 400 mm by 400 mm. So 400 by 400, you will get 16,000, 1,60,000 mm square area. I think somebody is waiting. Now this area, after computing the area, so next, length of the copper and cast sorry, this is not cast iron, copper and concrete rod is L is equal to 2 meters. So length it is given. So this length is equal to 2 meter here. So this is given. Length of the column is 2 meter. So length of the column is 2 meter. 2 meter is converted in terms of mm. So this is concrete. Is compressive load. So load is acting 300 kilonewton. So this is the load given, 300 kilonewton. It is converted in terms of newton. So you multiply 3000 into 1000. K is equal to 1000. So you will get 3 lakh newtons. And the relationship between the elastic modulus is given. This is ES is equal to 15 times of EC. EC stands for concrete and ES stands for rod. So this relationship is given. So everything, so you read the question properly and then write the given data. Once if you have written the given data, so next step is to analyze the mechanism. Say this is the column. So this is top view. Actually, I will draw the front view of a column. Approximately this is like this column. So it consists of some rods like this. So it's a continuous in nature. So I am simply representing by dotted. So this is loaded with 300 kilonewton. 300 kilonewton load. So assuming this end is fixed one. Now here see, so because of application of this load, so this deforms, change in length occurs, compresses, entire column compresses. So this is the amount delta. The compression of steel bar is equal to compression of concrete bar, because of application of load, both will deform, uh, deform by a length same, or both will displace by same amount of distance. So by using this concept here, a strain in uh, bar, steel bar, is equal to strain in concrete region. So that concept is used. Both material deforms axially by same value of strain in both material. Strain in both material is same. So therefore, strain in steel rod is equal to strain in concrete is equal to general strain. So same thing you can write in previous lecture also we have written. Stress is equal to Young's modulus is equal to E is equal to stress upon strain. This relation you know. By using this relation, so I want to write the equation in terms of this. This is strain. Strain is equal to stress upon E. So you can rewrite this equation like this. So same thing I have written. So strain is equal to, by using this relation, strain is equal to sigma upon E here. See, the strain in steel bar is equal to stress in steel bar upon Young's modulus of steel bars is equal to stress in concrete upon Young's modulus of concrete. The same relation is written in this form. Okay. So I hope you have understood this statement. So because of application of load, so both steel as well as concrete by deform by amount equal. So next, one more relation we have to. So there are two materials. One material is, this is steel. So one material is steel, other one is concrete. The strength of concrete is different and steel material is different. So therefore, so here the load shared by, to deform, so deform this much distance, so the different load is required for steel bar and different load is required for concrete. Concrete needs, so in generally you know, concrete needs more load to deform same distance, but less amount of load is required by the bar to deform same amount. So if you are considering same cross sectional area, so therefore, so by using this relationship, the based on the strength and material properties, you can write one more equation. So that is load shared between two materials is equal to load shared by steel rod plus load shared by concrete. So this is equal to total amount of load applied. So that again PS is equal to, you can write this PS in terms of, because in previous equations, so there is a relationship between stress and Young's modulus. So here this equation also we have to write in terms of stress. So therefore, so this P is equal to, or stress is equal to P upon A. So you know stress is equal to P upon A, and then you can write P is equal to, so you take this A this side, sigma into A. Same thing it is written here. So this load shared by steel rod is replaced by stress into cross sectional area of steel bar, and load shared by concrete is written as, so this is stress into stress in concrete into cross sectional area of concrete area is equal to total load shared by. So this is the second equation. So because in the previous equation, so there are two unknown parameters. So again I will go back. So here, see, there are two unknowns. One is stress is not known to us. Stress in steel bar, stress in concrete beam is not known to us. But Young's modulus already it is given. Relation between Young's modulus is given. Or you can write this equation like this also. Stress in steel upon stress in this concrete is equal to ES upon EC. ES upon EC. Now ES upon EC, you take here ES upon EC, so it is 15. So this is equal to 15. You can write that. I have written later on. So thus here there are two unknowns and one equation. Because to solve these two unknowns, at least we need two equations. So for that, so we have to develop one more relationship between stress and load. So same relation it is developed, and using equation 2 and 3, previous equation is 2 and this equation is 3, using 2 and 3, and for solving unknown sigma s, sigma c and sigma d. This is the procedure. Now we have two equations. Two equations can be solved simultaneously for obtaining the values of sigma s and sigma c as well as delta L. Now, so we have equation 2 in previous, it is written like this. So it is rearranged. Just now I have written sigma x by sigma c is equal to es by ec. So this is equal to 15. So now we got one relation. This is the relation between sigma s is equal to 15 times of sigma c. It means that the strength of steel, stresses in steel are 15 times more as than concrete. So this is the meaning of stress. So using equation 3, so we have a equation 3. In equation 3, sigma s is unknown, sigma a is known, cross-sectional area, cross-sectional area of steel bar is known. So that already we have written in previous slide. And this is cross-sectional area of concrete. So this you can have. So this is the area of bar, 4 bars area, steel cross-sectional area and area of concrete. So by substituting these values in this equation, so you will get one relation. So in this relation, you know sigma s, see here, sigma s is equal to 15 times of sigma c. You substitute this value. So here in this equation, after substituting this, so this equation can be rewritten as, see there, 15 into sigma c. Here I have written sigma s is replaced by 15 into sigma c. So this into this as it is, plus sigma c into 16,000 is equal to this. So on simplification, there is only one unknown here, sigma c. So I have added both these together and so determine the value of sigma c. Sigma c is equal to 30,000 divided by, so the whatever summation comes from these two, so that it is added directly here written, and this is equal to sigma c is equal to 1.07996 Newton per mm square. So this is the amount of stress induced in concrete. And similarly, once you know the strength in stress in concrete, so you can calculate stress in steel bar. So by using this relation, by sigma x s is equal to 15 into sigma c. So we know this value of sigma c, 15 into this. So this is the amount of stresses so that are induced in steel bar. So thus we have computed stress in concrete and stress in. Now what is asked here in the question? So it is asked load carried by each material and compressive stresses produced in each material and load shared by the material. Okay, so we have computed this part we have done, and the remaining part is load shared by the material. So for load shared by the material, we have a relation. Already we have developed a relation. Load shared by the material, see here, already we have written one relation here. The load is shared between the two material is given by this equation. So it is written in terms of stress, and same equation you use here. PS is equal to sigma s into AS. Already we know sigma s. So it is already calculated sigma s into AS. So you will get So this is the amount of load. Say this is, sorry, this is the unit is in terms of Newton. So this much amount of load shared by four rods. There are four rods. So all these four rods share this amount of load. So that is 8480.1. Now what is the amount of load shared by single bar? So that can be calculated. Load shared by each rod is 8840.4 upon 4. You will get around 2120.1 Newton. So this is the amount of load shared by a single column. So similarly, so you can compute the load shared by concrete is equal to stress in concrete into cross-sectional area. This is the stress. So already we have computed here 16.1994. So I have substituted here into 16,000. So this is the amount of load shared by the concrete wall. Now you take these two together, so you will get 30,000 something. So thus, so you will get you can find out the load shared by this steel bar and load shared by the concrete. So you can compute the load shared by both. So let us see one more problem of similar in nature. So first of all, so we'll read the problem. So two vertical rods are each fastened at their upper ends at a distance of 600 mm, at a distance of 600 mm. So this is given here. It is at a distance of 600 mm apart. Each rod is 3 meter long and 12 mm in diameter. Both have 12 mm in diameter and length is 3 meters. 3 meters in length. A horizontal rigid crossbar connects a lower end of the rods and on it is placed a load of 4,000. So these two rods are connected by a horizontal beam. So and this beam is loaded with 4,500 newtons. Crossbar remains horizontal. There is a one more condition. So this load is loaded on this in such a way that so this bar should remain horizontal. So likewise, we have to apply this load and find the position of the load on the crossbar and stresses in each rod. So here we need to find position and stress in each rod. One rod is of steel for E is equal to 1.996 into 10 raised to 5 Newton per mm square, and the other bronze for which E is this. So here it is a given data. So first of all, we have to write the given data. I think whether I have written or not. For this, I have not written, but it is expected that so you have to write given data. So I will write given data instead of writing there. Here itself, I will write. So this rod, so these two rods are apart 600 mm. So this given data I have presented here, and each rod is 3 meter long. So this length of the rod is 3 meter. So that is 3 meter means. So its length is always, we are converting this in terms of mm. So you convert this in terms of 3000 mm. So I'm not writing here mm. So you note down this is 3000 mm and long and 12 mm in diameter. This diameter of both rods have a diameter. So this is equal to 12 mm diameter. So diameter is usually represented by circular symbol phi. I will write 12 phi. So it represents circular in nature, and this is also having same dimensions, 12 mm dimensions. So both rods have 12 mm diameter. A horizontal rigid crossbar connects the lower ends of the rod, and it is placed a load of 4,500 Newton, 4,500 Newton, so that the crossbar remains horizontal. Always we have to keep in mind this should be horizontal. This should not bend. It should not, one end should not be in lower direction and other should be up. So it should be always maintained in the horizontal direction. This is the constraint. Find the position of the load where we have to apply the load to keep this rod in horizontal position. So where we have to apply, say at a distance x from one end, and from another end this is 600 minus x distance. So that let it be from one end it is to be loaded at a distance of x. So we have to find out x. So here what is x is equal to what? This is the one it is asked in the question. And second, find the position of the load on the crossbar and stresses in each rod. Stress in steel bar. What is the stress in steel bar? And what is the stress in bronze bar? So these three things we have to determine. Steel bar. Rod Young's modulus is given. Young's modulus of this is for steel. E of S I will write here itself. Young's modulus for steel, Young's modulus for bronze. So I have written everything on diagram and here, so you don't write in the same fashion. So as I have shown in the previous problem, so you have to write a given data properly at one place. So in this problem I am not writing. It does not mean that it is not required, but it is required every time. So you have to follow the systematic procedure. So you have to write the given data and convert all given data into a desired form. So either mm, either centimeter or meter, but all should be in same unit. So that is mandatory requirement and primary requirement before solving any problem. So once you have written this given data, so next step, you analyze this system properly. What is the given? So one end of this bar is fixed. See here, it is fixed. So you can look at this figure. This end is fixed. Means these two bars are subjected to load of 4,500 kilonewton. So it is loaded on this horizontal bar, and this bar always remains horizontal. If it remains horizontal means deformation in this bar is equal to deformation in this bar, or elongation of this bar is equal to elongation of bronze bar. Elongation, I will write EL, elongation. Elongation in steel bar is equal to elongation in bronze bar. So this is the concept we are using here. See, so it is fixed from the given data. So if it is loaded, so and one more constraint, always it should be horizontal. If it is horizontal means the change in length of a steel bar and change in length of the bronze bar should be same. This is the one relation you will get, isn't it? And again, second relation. So in every such problems, you have to use same relations. This is the one relation. And second relation, what is the load shared by? See here. So the material property for steel material is different and bronze material is different, and their strengths are different. So they have a different strength means, so they need different load to deform. Same amount of deformation, they need different strengths. So different strength means different loads. So second relation is load shared by steel rod plus load shared by bronze bar is equal to total load. So this is the one equation. So thus every problem, in previous problem also we have used same concept. You remember this load shared and these two equations, you can solve any problem. Now same problem, now I will go to the problem. and we will see how to solve this problem systematically. So first step, a cross-sectional area is given, because for both the material it is having a cross-sectional area pi by 4 into 12 square. So this is the cross-sectional area of the bar. Let the stresses in the steel and bronze bar be sigma s, stress is, isn't it? This is sigma s and sigma b respectively. Since the rigid bars remains horizontal, the extension of the steel and bronze bars are equal. So for that, see here, strain in steel is equal to strain in bronze. Same, the strain means elongation. Elongation in steel bar is equal to elongation. So the first relation it is used here. See, and now it is written in terms of stress. So here I have used the notation stress F instead of sigma. So otherwise I will write this sigma. Sigma S upon ES. So this is the same kind of relation we have used previously. Sigma B upon EB. PS is equal to ES and EB is given. So ES is 1.96 into 10 raised to 5 and EB is 0.63 into 10 raised to 5 Newton per mm square. On substituting ES and EB here and on simplification, you will get the relation. PS is equal to 3.111 into PB. So you got here I have written directly. So here you have to substitute this, sorry, this is sigma, this is sigma B. So here notations are changed. Sigma X so is equal to 3.111 into sigma B. This is the stress relationship we got. So after that, so the second relations, see, load on steel bar is equal to load on bronze is equal to total load. See, PS into AS. So this is stress actually, it is not a load stated by both sigma S into AS plus sigma B into AB. So using second relation, so what relation I have discussed here, see the load shared by load, we are referring P for load shared by steel plus load shared by bronze bar is equal to P. Same relation I have written here, see here. So PS is equal to sigma into A. So already I think it is not necessary once again, you might have understood. So but still I will write once again, because this is must say this is load shared by P is equal to sigma into A. So load shared by steel, so written by this equation, load shared by bronze is written by this equation is equal to total load. Now here area of cross section for both the cases is same. So that on substituting these values, so you will get, so this is the total amount of load, 4,500 Newton load is acting. Substitute the area and here sigma B and this is also sigma B. Now sigma B stress in bronze is equal to, this is 9.68 Newton per mm square, and we know the relation stress in steel bar is equal to 3.111 into 9.68. So this relation we have derived previously. So from that, so you can substitute here. So this value it is substituted here. So you will get 30.11 Newton per square. So this is the stress in bar. So first target is over. So because in problem it is asked to find stresses in each rod. So we have computed stresses in each rod. The next thing what we have to do, so we have to find the position of the rod on the crossbar. So for that, so now we have to do exercise. So for that, consider a equilibrium of the rigid bar. Let the rod be applied at x is equal to applied at x mm from the steel bar, taking the moment about the steel bar we have. See here what I will write this equation once again. So such that this is the resistance offered by the material. So that is equivalent to load in steel bar So this is load in brass bar, and here the load is acting at a distance x from one end. So that is 4,500 Newton load is acting, and this load is acting at a distance of, we are assuming that this distance is equal to x. Now you take the moment about any one point. I am taking the moment about this point. So this is the circle point. So you can write the moment, sum of the forces acting in upward direction. This is the clockwise and counterclockwise we can write. So this is PS into zero distance. So this is, I will write separately. This is PS into 0 plus, so because this moment is acting in this direction, so I am considering this direction counterclockwise as a positive. PS into force into perpendicular distance, so it is 0. Now force PB into perpendicular distance. Distance between these two is, these two rods are placed at 600 mm apart. This is given in the problem, 600 mm apart. So therefore, so this is PB into 600. So this is equal to, or you can write minus. So because this moment, so this force is creating moment in this direction, opposite direction. So therefore, either you take minus or you write equal sign. So take the data to the right hand side of the equation. So this is at a distance 4,500 into x. It is acting at a distance of x. So this is the moment equation. Same equation it is written here. PB into 600, because this term becomes 0. Say see, PB into 600. PB into 600 is equal to 4,500 into x. 4,500 into x. So by taking moment about this, so you know stress. Stress, or this is 9.68. Okay, stress and 400. This is equal to, this is load actually, it is not stress, load PB. Now we have to compute the PB. 9.68. Sorry, there is a mistake here. So we know the stresses. So once you know the stress, load acting on steel bar is equal to sigma s into AS. So that is sigma x is equal to, sigma s is known. So this is 30.11 into cross-sectional area 113.1. So this is the amount of load which is acting here. So that we have to consider here. This is 30.11 into 113.1 mm square. So you substitute here. So this is wrong. And sorry, it is written there 113. So it is not 9.6. This is 9.68. Okay. So here what we have to do, we have to write 30.11 into 113.1 into 600 is equal to 4,500 x. So here x is equal to, so whatever product it comes, product of these three divided by 4,000. So you will get some other value of x. So you calculate and put it here. So there is a directly stress value is substituted here instead of stress. So we have to substitute the load value, load said by this, because this is in terms of load. So we are not considering here stress. So we are considering stress means, load. So here also we have to consider load. If you are considering stress, then it's okay. But we are not considering here stress. So here it is considered load. So here also we have to consider load. So the moment equation is force into perpendicular distance. So therefore, always we have to consider force. So this 9.68 is not a force. So this is stress. So therefore, So this is wrong. So you replace this by 30.11 into 11.3.1 into 600 is equal to this, and you write here equation. So this just simply you replace this by 30.11 into 113.10 into 600 by 400, whatever value comes. So that is the location of x. So from this end, left end, to this point, the same thing we have shown in the figure. Initially we have assumed, so this load is acting at a distance of x, whatever value of x you are getting, so that is this value. So thus, so this is a simple concept. You can understand this mechanism, so you can easily solve any kind of problems. So I hope, what is the time now? Now time is around so 44. So okay, so just I will give you hint. I hope time is over, since from 3 hours you are continuously attending the lecture. So I will give you one more problem. So I will explain this just a concept and do the calculations. So such that I am not going to repeat such kind of problems again and again. So those who have missed yesterday, so they can also understand the concept of such kind of problems. Now here, a rigid bar AB, 9 meter long, is suspended by two vertical rods at its end and a horizontal position under a load P as shown in figure. Find the position of the load P so that the bar AB remains horizontal. Here also same thing. So there we have, in previous problem, we have two bars of same length, but here we have bars of different length. Here one has 3 meter length and second bar has 5 meter in length. So thus the length of the bars are different. Here see 3 meter and here it is 5 meter. And cross sectional area, in previous case both bars have same cross sectional area. Now in this case the first bar has different cross sectional area and second bar has different cross sectional area. Again the material is different, here also, here also. And here also we have to find out the location of force. Yes, same principle. And here also, so we have to keep, see this, it is mentioned in the problem that, so always this bar is kept horizontal position under a load P. So this always we have to keep horizontal position. If you are keeping horizontal position, so length extension of this bar is equal to extension of this. So therefore the first strain in bar 1 is equal to strain, say I am referring this as a 1 bar and this as 2. See, strain in bar 1 is equal to strain in bar 2. Same relation, the same kind of relation we have used in previous also. And second, see, to find the force, so again we have to take the ratio, or we solved the problem in previous way, so that way also you can solve, and this way also you can talk. The ratio of force P1 by P2 is equal to, so distances, corresponding reciprocal distances we have to take. Force into moment, see, in other words I can call the moment caused by, so this force must be equal to moment caused by this force, so that is equal to this. So therefore, so here you can write force into perpendicular distance, force in steel, and force acting in, say, C. So I will write, so this force into perpendicular distance, PS into X, is equal to 9 minus X into PC. So you take the ratio, you will get this equation. You substitute this equation here. So only one relation is sufficient here. Delta L1 is equal to delta L2. So you write delta L1, delta L2 equation here, and substitute the corresponding value of P1. Say this is P1 is equal to this much. Here you substitute P1. So entire equation is in terms of single parameter. Simplify. So you will get the value of X is equal to 331. So this is the way. Same concept you can apply to the previous problem also for getting the value of x. So it doesn't matter. So you can use either this way or that concept. So both are valid, whichever you find convenient. So you can use this. So this is the way. So any kind of problem you can solve which are belongs to dissimilar metals, composite materials. So this I have taken around 4 numericals on this. I think these all numericals are based on same concept. So only thing is you have to understand the mechanism. So that is most important. So I think let us will stop here itself. Print screen. Hi, just a minute. I will clarify your doubt. So I'll take a snapshot. Yes, yes, please. Yes, huh. Example 8. Okay. Example number 8. This is na. Huh. टोटल टोटल एरिया म्हणजे टोटल एरिया घेतला बरोबर सांग तुझं काय डाऊट सांग हो 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 यू आर राईट परफेक्ट हा स्टील मधून ह्याच्यामधून मायनस केलं पाहिजे -78 ओके ओके यू आर राईट 78522.5 okay you are right good all of you listen so this is the one mistake I have considered entire area so we have to subtract the cross sectional area of steel from this so that gives the area of concrete okay so it's right now here we have to make the corresponding changes everywhere so ha corrections karun घ्या सगळ्यांनी so you are right so any doubts any other things so we missed बरोबर आहे काय नाव तुझं हॅलो रोहित okay good so it means that you have understood the problem properly so okay perfect because we have considered the area twice because here we have to subtract this and we have to consider the area so हा एरिया कुठे कुठे यूज केलाय आपण कॉन्क्रीटचा इथे एक एरिया यूज केलाय इथे चेंजेस करावं लागतील आणि कुठे यूज केलंय हियर त्याच्यामुळे हा दोन्हीचा सम बरोबर आलेला नाही से 25 प्लस 8 नाही आलेलं 30,000 पाहिजे ना इथे सो हा व्हॅल्यू जास्त आलेला आहे त्याच्यामुळे चुकीचं आलेला आहे सम ऑफ दिस पीएस प्लस पीसी इज इक्वल टू 30,000 यायला पाहिजे होतं हा आलेलं नाही सो बिकॉज ऑफ दॅट आय थिंक okay you recalculate this problem once again so I will modify this and I will share later on okay see okay now I will stop sharing